everyone, my name is Joana Marieton P. Inoferio, and we are Group 3, here to present about what influences the movement of heavenly bodies. But before we start our lesson, I would like to have a very simple question. What is motion? That's right! In physics, motion is the change of position in an object with regards to its surroundings and in a given time interval. Now that that's out of the way, let us proceed to our first lesson of Module 3. So the first lesson is circular motion. So what is circular motion? Circular motion is defined as motion of a body along a circle. It can be a carousel, a car going roundabout, a moon orbiting the Earth, or the Earth revolving around the Sun. So, uniform circular motion is a type of circular motion. It is defined as motion in a circle at a constant speed. Example is a car moving in a circular path at a constant speed of 40 kilometers per hour. Is an example of an object in uniform circular motion. This means that every point of the circle, the car would be moving at 40 kilometers per hour. The velocity of the object moving in a uniform circular motion is always tangent to the circle. The magnitude of the velocity vectors corresponding to the speeds are equal. The speed is constant for uniform circular motion. With these information in mind, we can sum it up with a formula, which is velocity equals 2 pi r over time. The time, or t, needed by an in-uniform circular motion to complete an orbit is called its period. The distance is the circumference of the circle with the radius, or r, given as 2 pi r. Here is a sample problem. A car is traveling at 9 meters per second in a circle that has a radius of 60 meters. What must be the minimum value of coefficient of friction for the car to make the turn without skidding? The given are velocity equals 9 meters per second and radius, which is 60 meters. What we need to find is the coefficient of friction. Coefficient of friction equals velocity squared over radius times gravitational force. So the coefficient of friction equals 9 meters per second squared over 60 meters times 9.8 meters per second squared, which is 81 meters squared over s squared over 588 meters squared over s squared. And we will proceed to cancel these out. So, as a result, the coefficient of friction is 0.14.
So hello everyone, for the next lesson we are going to talk about centripetal acceleration. So what is centripetal acceleration? Centripetal acceleration is the acceleration experienced by an object moving in a circular path. According to Newton's second law of motion, which is law of acceleration, the net force acting of an object is equal to the mass of the object multiplied by its acceleration. It is important to note that centripetal acceleration is not a force, but a measure of the change of velocity of an object moving in a circular path. So the magnitude of centripetal acceleration can be calculated using the formula of A equals V squared over R, whereas A is the centripetal acceleration and V is the velocity and R is the radius of the circular path.
Hello everyone, my name is Nethan Banua and I am our next lesson presenter. So our next lesson here is all about centripetal force. Centripetal force is the force in objection to move in a circle at constant speed. The force is directed towards the center of the circle. Here is a sample problem. A 400-gram rock attached to a 1-meter string is whirled into a horizontal circle at a constant speed of 10 meters per second. Neglecting the effects of gravity, what is the centripetal force acting on the rock? So, here is our given. V is equal to 10 meters per second R is equal to 1 meter and M is equal to 400 grams or 0.4 kilograms. To solve for centripetal force, we must use this equation. Centripetal force is equal to mass times velocity squared over radius. We just substitute the numbers so that we will have 0.4 kilograms times 10 meters per second over 1.m. And we just cancel out the 1.m with the meters above. And after solving for the solution, our centripetal force now will be 40 kilograms point times 40 kilograms times meters per second squared.
So let's move on to the next lesson, which is centrifugal force. So what is the definition of centrifugal force? It is an apparent force that acts outward on a body moving around the center. So I will explain to you what is going on with centrifugal force. If centripetal force is the force direct towards the center of the circle, centrifugal force is the reaction force to it. The centrifugal force does not act on the same body as does the centripetal force. It acts on the same string, while centripetal force acts on the object. Since centrifugal means fleeing from the center, so the centrifugal force acts away from the center. This means that if the string cut, the rock will not fly away from the center, rather it will move tangentially on the circle. That's it. And this will be if the rock will be cut tangentially, and the force will go, so this is centrifugal force on the rock, and this will be the centrifugal force on the string, and this is the rock, and it will cut tangentially. So that's it. That's the lesson of centrifugal force. Thank you.
Laws of planetary. Aristotle. The Earth was the center of the universe. The Earth is at rest, that when an object is thrown vertically upwards, it will return to the Earth. Heraclitus. The Earth turned on its axis. Aristarchus hypothesized that the Earth moved around the Sun. Plato. Since God sheltered man on Earth, then it should be the greatest planet, and therefore the center of the universe. Claudius Ptolemy. The stationary Earth was at the center of the universal, and all planets move around it in epicycles. Geocentric Earth centered. Tycho Brahe built huge protectors to see the exact location of the stars. He was able to locate the position of some 1,000 fixed stars. He was considered the last great naked eye astronomer. Francis Kepler, an advocate of the Copernican system, used the planetary data handed to him by Brahe, which led him to conclude the Copernicus theory was right. He made mathematical calculations and then concluded that the planets follow a path similar to a geometric figure known as ellipse. Kepler's law of planetary motion. The first law, the planets move around the sun in curved paths, which are not circles but ellipses, and the sun is located on one of the ellipse's foci. The second law, a line drawn from the center of the sun to the center of any planet sweeps out equal areas of sky in equal time as the planet revolves around the sun. Law 3. The time for each planet to revolve once around the sun is related to its average distance, r, from the sun by a formula T2 equals kr3, where the constant k is the same for all planets including the Earth. Additional resources. Galileo, who lived during Kepler's time, knew Kepler's work but never fitted these ideas into his own theories about motion. The man who finally put all this together in order to formulate the law of gravity was Isaac Newton, one of the greatest scientists of all time.
Hello everyone. Now today I'm going to discuss Newton's law of universal gravitation. Every object in the universe attracts every other object with a force that is directly proportional to the product of the masses of the two objects, and inversely proportional to the square of the distance between the centers of the two objects and in a line connecting their centers. So our formula for this is F sub g, which is the force of gravity, equals G, which is the universal constant, which is equal to 6.67 times 10 raised to the power of negative 11, n times m squared over kilogram squared. Times m1 times m2 over r squared, which is the distance between two bodies. Now for a sample problem, determine the gravitational force between a 60 kilogram and a 70 kilogram person who are both standing 2 meters apart. Given m1 is equal to 60 kilograms, m2 is equal to 70 kilograms, and r is 2.0 meters. Find the force of gravity. Solution. F sub g is equal to g times m1 times m2 over r squared. F sub g is equal to 6.67 times 10 raised to the power of negative 11 times n times m squared over kilogram squared times 60 kilograms times 70 kilograms all over 2 meters squared. Now, F sub g is equal to 28,014 times 10 raised to the power of negative 11 times n times m squared all over 4m squared. Now we cancel the m squared, so we were left with F sub g is equal to 7,003.5 times 10 raised to the power of negative 11 newtons. So the total of this is F sub g is equal to 7.0 times 10 raised to the power of negative 8 newtons. Henry Cavendish determined the universal constant and made possible to accurately determine the mass of the Earth. M sub E equals 5.98 times 10 raised to the power of 24 kilograms. The law of universal gravitation is used to estimate the acceleration due to gravity near the surface of the Earth. It is found using the formula G equals uppercase G M sub E over R sub E squared.
The next lesson is all about gravitational field strength. Any object of mass experiences a force exerted by the Earth's gravitational field. A gravitational force of n.8 Newton is exerted on each kilogram of mass, and so the Earth's gravitational field strength is 9.8 Newton over kilogram, which is equivalent to 9.8 meter per second. The acceleration due to gravity, which is presented by gravitational field. For convenience, both the gravitational field strength and the acceleration due to gravity can be rounded up to 10. Mass and weight. Mass is the measure of inertia of an object. The greater the mass of the object is the greater in the inertia, and the more force is needed to change its state of motion. The mass of the object can be found using a balance, and it's measured in kilograms. Weight is a force. It is another name for the Earth's gravitational force on an object. It is measured in newtons like any other force. The term mass and weight are often used interchangeably, but there is another clear distinction between them. Mass is a property of a body itself, while weight is the force of the gravity acting on a body. Unlike the mass of the body, which is constant, weight varies with location.